Okay, good morning, everyone. Whoever is present. Okay, so this is where we had stopped. This was the last slide of last week's class that concerns that, for example, the Ehrenfest-Stern model is irreducible and recurrent. So today we will have a look at another model which we had studied earlier, the gambler's ruin model. So recall that this is a simple random walk with an absorbing boundary at 0. So it's a random walk on the set 0, 1, 2, 3, etc. And 0 is the absorbing boundary. So in particular, it's a birth-death Markov chain with one absorbing boundary. Okay. So that's what I have written. And since it's an absorbing boundary, 0 is an absorbing boundary, P00 is equal to 1, and P0j is is 0 for every j bigger than 1. So in other words, if the process goes to the state 0, then it just stays there forever. And of course, at for I greater than or equal to 1, it is just like the simple random walk. Pi plus 1 is Pi, of course. That is in turn, this is the using the notation of the birth-death chains. This Pi is the same for every I. So let us denote that by little p, which is strictly positive. And Pi minus 1, that is Q, which is 1 minus P, which is also bigger than 0. And of course, therefore, Ri is 0 for every I greater than or equal to 1. Please note it down if you want. Okay. So note that the gambler is ruined whenever xn becomes 0 for some n greater than or equal to 1. So consequently, if the gambler starts with an initial capital of K, then the probability of his reaching 0 in finite time. So once that he reaches the capital 0, then he stays there forever. So that is same thing as probability of absorption at 0.
Sir, I have a question.
Yes.
So have you started the class just now?
Yes, just I explained again the notations of the gambler's model.
Okay. So what is the first slide?
Huh?
What is the first slide?
First slide was the last slide of the last class.
Was the last of the last class. Okay. So basically you are explaining gambler's win model, right?
Yes, correct.
Okay. So which has been covered in the last class?
Huh?
Which has been done in the earlier classes, earlier lectures.
Yeah. I mean, I suppose you must be familiar with the various examples we had given, no?
Okay. So regarding gambler's win model, okay, fine.
So it's a gambler who is sort of betting against an infinitely rich adversary. So this is a particular case of birth-death Markov chain with absorbing boundary, and absorbing boundary is 0, and the state space is this. And here are the various one-step transition probability. And here that P sub I is same for every I for I greater than or equal to 1. So that is P, and Pi minus 1 is Q. Ri is 0 for every positive, every non-zero I. Okay. So the probability of gambler's ruin if he starts with an initial capital K, is same thing as rho K0. That is rho K0, recall, is the probability that starting from K, the process reaches 0 in finite time. That is the problem. So our objective is to find this. Now you can easily guess what we are going to do. So in the argument which we had used in the unrestricted birth-death chain, take that capital C equal to 0 and consider the case of one is beginning with any K which is strictly positive. So that is our rho K0. Yeah, please note down if you want to. So hence for K greater than or equal to 1, taking C equal to 0 in that equation which we had denoted by Sweat suit, and also in that equation using the additional information that we have, that Pj equal to P for all j greater than or equal to 1, and similarly Qj equal to Q for all j greater than or equal to 1. Then so as before, rho K0 is nothing but limit as d increases to infinity of P sub K, T sub 0 strictly less than Td. The same type of things we had done earlier. And I think in there we had denoted this by some psi k or something like that. So we had derived an expression for that. You plug that in that expression and use this information. So therefore, that those expressions which looked rather forbidding or rather long in the case of birth-death chain, that reduces to such a simple expression. Okay. So you can, I think, replace this we get by verify that. Okay. Whenever say we get or it is easily seen, note that, observe that, all these basically means verify that. So that is limit d going to infinity of this expression. So here this is j going from 1 to d minus 1, and here it is k to d minus 1. So that is the dependence on k here.
Sir, just for clarity, so what is capital D here?
Capital D is some number we are taking greater than 0. So just like the other case, no, C was less than D. And anyway, it is limit D going to infinity. So that limit expression will not
okay. So basically capital D is greater than 0.
Yes.
Okay, fine.
Now note that, so here we are having, and here it is a finite series. Of course, as d goes to infinity, this will be an infinite series. It's a geometric series. And if that series diverges, that is summation j going from 1 to infinity, q over p to the power j, that is equal to infinity, then this ratio would be 1. And when will that go to infinity? If this q happens to be bigger than p. That is, you remember that the geometric series, the infinite series converges if the common ratio is less than 1. So this, if it exceeds, it is not less than 1. So that is, if it is greater than or equal to 1, this is going to diverge. And that can take place only if P is greater than or equal to Q, which means P greater than or equal to half. If it converges, then this expression would be finite and less than 1. And also, if it converges, you can easily check that this expression is precisely this. So the probability of gambler's ruin, if he starts with an initial capital K, is 1. If his probability of winning any bet is less than or equal to half. If it exceeds half, there is a slight chance that he might sort of be able to play for a long time. But his fortunes might wildly fluctuate. So please note down if you want. All right, let us go to the next one. Note it down. So we are now going to look at what are called absorption probabilities. Oh, I think there is a spelling error here. Probabilities, L-I-I have omitted. Please make the correction.
Sir, I have a question. So is the absorption probability defined only when Markov chain has finitely many transient states, or it may have infinitely many transient states?
That's what I'm coming to.
Okay.
Okay, suppose Markov chain has finitely many transient states. Then being able to compute the probability of absorption into a set, when it is getting absorbed means what? It enters an irreducible closed set. See, the state space might consist of recurrent states and transient states. And the set of all recurrent states we have seen can also be decomposed into a finite or countable number of mutually disjoint, irreducible closed sets of recurrent states. So if that irreducible closed set of if one of those closed sets turns out to be a singleton, then that particular state is an absorbing state. If it has more than one element, then in that irreducible closed set of recurrent states, the Markov chain will be visiting all the states inside that infinitely often with probability 1. We have seen that. So probability of absorption in an irreducible closed set is sometimes an useful information if you can find. Of course, one may be interested even if there are infinitely many transient states. As a matter of fact, in the gambler's ruin problem, that's what we have done, right? The gambler's ruin problem. So this what we were interested in. Okay. So if the state space itself is finite, then there is at least one recurrent state, and hence there is at least one irreducible closed set of recurrent states.
Sir, I have a question. So in gambler's ruin problem, so which are the recurrent states precisely?
There are no recurrent states. Recurrent state is only that 0. If it reaches 0, it keeps coming back to zero again and again. And so therefore, starting from zero, the probability of reaching zero in finite time is 1. So that is a recurrent state.
Okay, but no other state is recurrent. Means 1 to everything is transient.
No, yeah, everything else is transient.
Okay, because from zero we cannot reach any other state.
Yes.
Okay, fine.
And of course, from any k, there is a positive probability of reaching zero.
Yeah. So basically, Gambler's-Lewin model, we have infinitely many transient states.
Yes, of course.
Okay.
Yeah, we have proved that for any birth-death chain with on 0, 1, 2, etc., with 0 as absorbing state, right? When we considered birth-death chain with the one absorbing boundary at 0 in that positive non-negative integers, that is what we had proved. The general result. Only 0 is a recurrent state, all the other states are transient.
So, sir, if a Markov chain has an absorbing state, then only that state can be recurrent. All others will be transient.
No, not necessary.
No, but I am saying if the Markov chain has an absorbing state, then that state will be the only recurrent state.
No,
Others
state will be recurrent, but there could be irreducible closed set of recurrent states.
Yeah, there can be irreducible closed set, but starting from that absorbing state, how can we reach any other state with a positive probability?
Yeah, you will not, because but then so the absorption state will be one such case, and an irreducible closed set of recurrent states can also the process once it reaches, it cannot come out of the closed set, but within that closed set it can be keeping on moving. No.
Okay.
This irreducible closed set can contain 2 elements, for example.
Yeah.
Then neither of them is an absorbing state.
No, neither of them is an absorbing state. Yes.
But they are recurrent states.
Okay. So basically, an absorbing state is an irreducible closed set of cardinality 1.
Don't unnecessarily impose terminologies. Okay.
So basically, there may be recurrent states other than absorbing states.
If you do like that, that would be more confusing than being transparent.
Okay. But I am saying that there can be recurrent states other than absorbing states.
Of course.
Okay, fine.
Any absorbing state is a recurrent state, but converse is not true. Okay. So if the state space itself is finite, then there is at least one irreducible closed set of recurrent states. So we are going to present one result. The parts that result consists of 3 parts. The first and the second part, that set of transient states need not be finite. Okay. So this is the result. Let C be an irreducible closed set of recurrent states for a Markov chain Xn. And denote by Tc the hitting time of the set C. That is the minimum n greater than or equal to 1 such that Xn is in C. So that is the first positive time when Xn comes into C. That's what the hitting time. And let us denote by rho sub C of X, probability Tc is finite given X0 is equal to X. So this is the probability of eventual absorption in this closed set C starting from X. If the C is a singleton, then that is the probability of absorption in that absorbing state.
So what do you mean by eventual absorption? Means absorption after finitely many steps.
Finally, but then finally, I mean, it eventually means at some finite time it enters that, after that it doesn't come out.
Okay.
Okay. Then the following statements hold. So that is, we are going to talk about this as a function of function of X. So rho sub C of X is equal to 1 if X is already in C. And rho sub C of X is equal to 0 if X is in SR, that is, if X is a recurrent state, but that is not an element of this particular irreducible closed.
So that means X is part of some other irreducible closed set.
Yes.
So that's why it will be 0. Okay.
So actually, these two are practically obvious statements. Now, if you consider, please note down a few. So as I told you, we are going to consider this rho sub Cx as a function of X. So now, say in this first statement, we have given all the information concerning when X is a recurrent state. If X is an element of C itself, then it is equal to 1. If X is a recurrent state but not in C, it is equal to 0. So the main part of the theorem concerns when X is a transient state. So as a function of X coming from S sub T. So consider the function X going to rho sub Cx as a function on S sub T. Then this function satisfies this equation. Rho sub C at X is equal to summation Pxy with Y varying over C plus summation Y varying only over St P sub Xy rho sub C of Y. So rho sub C is occurring here, rho sub C is occurring here. So this is a kind of functional equation for rho sub C on St.
Sir, can you explain this equation? It is not quite clear to me why this holds.
If you think a bit, it is clear. It will also be, you will see in the proof. If you can immediately see what this means, you get a proof. You get the picture. If you get the meaning of this, you will soon see. If you are sort of able to see what this exactly means. Okay. Now the third part. If the set S sub T is finite, then if you consider this function, X going to rho sub C of X as a function on St, it is the unique solution to this system of equations. Take, supposing F is a solution to this equation, F of X equal to summation Pxy, Y varying over C, and then summation Y varying over S sub T, Pxy Fy, and Y varying over S sub T.
So basically, sir, in this system of equations, so pxy they are basically constants.
Pardon?
Means the pxy they are known constants. Means
Let's say the
they are known.
transition probabilities.
Okay. So basically, we are solving for fx, fy, those things.
Not fx, fy, those things. We are solving for f.
Yeah.
F is the function. We are wanting to get hold of that function on st.
St. Okay. But why are we taking st finite in this case?
You will see.
Okay.
See, if you are able to solve this equation for some, in that sense, some context. Let's say you don't have any information as such about rho sub c, but you are able to solve this. Let's say you also know what the set st is. Then if st happens to be a finite set, then we can conclude immediately that this f has to be rho sub c. In other words, uniqueness of this system of equations, one may not be able to guarantee. Okay.
So basically, we'll prove that the system of equations is consistent with the unique solution.
If it is finite, we prove that this f has to be.
Okay.
Don't bring in words like consistent and things like that. Those things can mean many things in many contexts. Okay. So let us take up please note it down if you want. So part 1 is easily seen. As we were writing it down, we have basically proved it. So let us take up the part 2. Let us say x is in st. So remember, our rho sub cx is this function. So this tc can be any integer greater than or equal to 1 or possibly infinite. So tc can be equal to 1, equal to 2, equal to 3, equal to 10 million, and so on. So consider the probability p sub x tc equal to 1. So which means, that is the starting from x, the process reaches c in the very first step. And the one step starting from x, it has to be some xy, pxy. And if you sum over y going through c, that precisely is this problem. So the first term which you saw in the equation is precisely p sub x tc equal to 1. So that is what was occurring here. So this is a probability that probability tc equal to 1 given x0 equal to little x. Okay. Now we are trying to see what this is. Probability tc is greater than or equal to 2 but finite. Given x0 equal to x, the starting point is x. And if y happens to be, so that is, then this will vary over various y's in the first step. But then y coming from C itself will not figure in this, because if y comes from C, then that is taken care of here. Okay. So therefore, this is here, the y is varying only the complement of C. If y comes from C, then that will not occur in this event. It will be taken care of here.
So basically, we are considering two disjoint events and summing their.
Please. Yes, correct. All right. Now, here, use the Markov property. T2 less than or equal to Tc is less than infinity given x1 equal to y and x0 equal to x. Then in this case, this information is irrelevant. It is enough if you know if we are this thing x1 is y starting from y, and also homogeneity. And when you are going to consider it as starting from y, then this is just Tc less than infinity. And what we have written here, okay, that is precisely is rho C y, rho sub C y. But rho sub C y, when y comes from other recurrent states, that is here, we know that is 0 from part 1. That is why we are saying, using the Markov property we have used here, and this and part 1 we are using it here. Yes, difference C, the set minus S minus C is precisely ST union SR set difference C. This is a disjoint union. And on this set, this portion, this is going to be 0. Because once you are in some other recurrent state outside of C, you cannot come back to C. So you have, please note it down if you want. Consequently, rho sub C of at x is probability Tc equal to 1 given x0 equal to x plus probability 2 less than or equal to, that is Tc greater than or equal to 2 but finite, given x0 equal to x. So the first one we had found here, and the second one we have found in the other one, and that precisely is this is what we want to prove. So this proves part 2. Note it down. All right. So first of all, note that by part 2, one knows that this function x going to rho sub C x satisfies that system of equations which we have denoted by bullet. See, this equation, these are sort of very the same. So if you have shown here that rho C of x satisfies this, so that means this is rho sub C of x is the one solution of this equation. So proving the part 3 basically implies that for this equation, uniqueness can be proved if ST is finite. So the proof of part 3 basically involves this system of equations has a unique solution. And since we have proved in part 2 that rho C is one solution, then concluding that solution is rho C. So this will be useful if you are able to get hold of a solution of this set of equations. Wherever that is possible, this information will be useful. Wherever you may not be able to easily solve this system of equations, this result is not going to be of much use. In that case, one should look for other means of trying to find rho sub C. Okay.
Sir, I have a question. So can you go to the last slide? Just means why? Yeah. So in this equation, in the first summation, we are taking care that in the first step, we are from a state in ST, we are going to a state in C. And in the second summation, we are going from a state in ST to another state in ST. But it may happen that from X, we go to a recurrent state which is not in C. Then what will happen?
Has been rolled out here. See, this summation, okay, this includes SR difference C, but here this is missing, right?
Okay.
Why did we do that? Because this, yes, when that Y, this thing is in, Y is in, yes. See, remember, this is rho C of Y. This expression is rho C of Y.
Yes.
So what we have written here is actually equal to such an expression plus another such expression with Y varying over this guy, this set. And for such sets, rho C Y is 0 is taken care of by part 1. Those are
Okay,
0.
sir. Okay, sir. Got it, sir. Got it. Got it.
If you are writing down notes, you can immediately see. That's why I'm going slowly and giving you time to write. Please bring some paper, pen and all that with you and if you want to take down notes. Okay. Now, let X be an element in ST. Note that TC equal to 2 and X0 equal to X is that event is same thing as X2 in C, X1 not in C, and X0 equal to X. If X1 is in C, then that will be covered in the event TC equal to 1. So P sub X TC equal to 2 is probability X2 in C, X1 not in C, given X0 equal to X. And when X1 is not in C, either X1 is in ST or X1 is another recurrent class. So now use Markov property here. By Markov property, this is just probability X1 in C given X0 equal to Y. I have skipped one step in going from here to here. So you can please supply that step. And probability X1 is in C means probability X1 equal to Y for some, Z or something like that in C, and X0 equal to Y. So this Pxy and what you get by the Markov property, that precisely is P sub Yz with Z being in C, because X2 is in C. So I should say perhaps using a Markov property, etc., verify that. How we get this step from this here is an exercise for you. Please note down if you want. So I hope you have copied, those of you who want to. But here, note that if Y is in SR set minus C, that is, it is a recurrent state, but it is not in C, Pyz and Z is in C, Pyz will be 0. Once you are in SR difference C, you cannot come to C. So this will be 0 for all Y coming here. So therefore, this will vanish. That's what I have written here. This follows from part 1. So basically, we have P sub X Pc equal to 2 is just this expression. Next, also note that Pyz equal to 0 if yes, if Y is a recurrent state and Z is a transient state. I mean, this Y and Z are not related to the YZ occurring here. So in other words, if X is a transient state and Z is another transient state, P super 2 ZX, XZ. That is probability of coming from one transient state X to another transient state Z in 2 steps. What this means is it can happen only if through another intermediate transient state. If Y happens to be a recurrent state, it will get caught in that class, irreducible closed set of recurrent state class where it is. It will not come out. You know, in general, P super 2 xz is summation over y varying over all whole of S. But if these two are in transient state, all the intermediate fellows will also have to be transient states. So the thing to observe here is that in this kind of a thing, all the intermediate things also have to be transient state. That is the sort of the unifying aspect of these two steps. So one can easily obtain analogous conclusions for P sub x, Tc equal to K, and also P super K x z. And we will stop here for the day. So we still haven't proved part 3. Some more work is needed. We have to sort of pull together this information, all this information.
So is today's class over?
Yes, modulo you are wanting to copy and things like that.
Okay. So will you finish the proof in the next lecture?
Of course.
Okay.
It is not such a monstrous theorem which goes on and on for several classes, okay? It's a fairly simple result. Many things are simple because I can do only simple things. I cannot do very complex things. Okay, I'll stop sharing.
Sir, I have a question. So will you give another problem set before the midterm exam?
Of course, I will.
Okay. Means it will be good if you can give another problem set. Okay.
Sure. Okay, I shall end the session now.
So, sir, I have a question. So the difficulty level of problems in the mid-sem will be similar to that in the problem set?
I hope so.
Okay, fine.